Integer exponents. What is an integer and what are parts of a power? Well, we need to understand that there are different parts that make up a power. We have the small number on top, which is considered the exponent, and the big number right here, that's called the base. Now, both parts altogether are called the power. So we've got to make sure that we understand our definitions. So integers we know as positive numbers, negative numbers, and zero. So let's talk about each one of those separately. Let's start with positive exponents first. Positive exponents show repeated multiplication. So when we have something like 2 to the 5th power, it is basically telling us that we will have 2 5 times. And then we would multiply them together. 2 times 2 is 4, 4 times 2 is 8, 8 times 2 is 16, and 16 times 2 is 32. So we keep that in mind that that's how that works. Now, for my class, let's just keep it simple. If we have exponents that are 4 or less, I expect you to simplify it just like I did right now. If we have exponents that are 5 or more, you could leave it alone. Because if we got something like 7 to the 8th power, without a calculator, it would be very difficult to figure out. So we'll just leave it alone and simplify it that way. I think that'll work out best for us. Now let's practice here a little bit. Here we have 3 to the 4th power. That tells us that we have 3 times 3 times 3 times 3. We know that 3 times 3 is 9. And here I have 9 times 9 is 81. You see me showing a different way to group this and explain it instead of going straight across like I did a moment ago. Remember, with multiplication, because of the commutative property, I can multiply them in any order that I want to. I don't necessarily have to go left to right. Here in example 2, I have 5 to the 2nd power. This is 5 times 5. And we know that 5 times 5 is 25. So hopefully that kind of explains our positive exponents. So now let's talk about the negative exponents, which are the opposites of positive numbers, aren't they? Well, we know that when the exponent is positive, we multiply the base by that number that many times. Now, when the exponent is negative, we do the opposite. Since positive and negatives are opposites, we divide the base by that number that many times. Now that may seem a little bit confusing, so let me give you a little side rule that I've come up with. Basically, when the exponent is negative, we know that the power is basically located in the wrong place. Instead of being in the numerator, it should be in the denominator. So let's move it first. In other words, take the reciprocal of the number, then evaluate it. Once you take that reciprocal, that exponent becomes positive. You'll see what I mean here in a second. So let's say, for example, this 8 to the negative 2. We know that all numbers are over 1. And because of this negative exponent, we need to take the reciprocal of this number. We do that. We put 1 over 8 squared. And once we take the reciprocal, that exponent that was negative now becomes positive. And then we'll continue on and simplify this. 1 divided by 8 times 8, which is 64. Now let's try it one more time. We're going to do a little bit opposite here. Here I have an example of 1 divided by 8 to the negative 2. Now, when we talk about 8 to the negative 2, again, we're thinking, hey, it's in the wrong place. That's true. Let's take the reciprocal. Once we take the reciprocal, it becomes positive. Now, I can put it over 1, and I don't necessarily need to show this divided by 1, do I? Okay? And then I can continue. 8 times 8 is 64. So that might help a little bit more than actually knowing all the definitions. Okay? Let's do one a little bit more involved so that we understand where everything comes from and how it all works. When we're evaluating this, we can see that the P here has a negative 9 exponent. The Q has a negative 4 exponent. Here in the denominator, the R has an exponent of positive 2, and the S has an exponent of negative 3. Now, I don't want to take the reciprocal of this whole thing because not every base in this fraction has a negative exponent. We can see that this one, this R squared, is a positive exponent. And because of that, we're not going to move that one. We're going to leave it exactly where it is, which is in the denominator. It doesn't need to move. But this s to the negative 3 needs to move from the denominator to the numerator. So we'll put that up into the numerator and make that positive. This p to the negative 9, we need to move it from the numerator down to the denominator. Same thing with the q to the negative 4. They both need to move. So let's move them both into the denominator. And once we do that, now all the exponents are positive. Now, if we had bases that were numbers instead of letters, we would continue in simplifying this. Now let's talk about zero exponents. The rule is that any base to the 0 power equals 1. And for right now, I just want you to kind of go with me and accept that, and I'll prove to you in a little bit here why that's true. So if we see 3 to the 0 power, we know that that's going to be equal to 1, no matter what. The same thing is true with a to the 0 power. So any base with an exponent of 0 will always equal 1. So let's look here at example 6. We have 5 times a to the 0. This is saying that I have a base of 5 with an exponent of 1 is being multiplied by a base of a with an exponent of 0. Well, we know 5 to the first power is 5, and a to the 0 we know is 1. And 5 times 1 is 5. So this whole thing here, 5a to the 0, really means 5. Let's try it again here in example 7. Again, let's break it apart. We have 3 squared times x squared times y to the 0. Here we have 3 times 3, which is 9, x times x, which is still x squared, and y to the 0 power, which is 1. We're going to combine like terms, so we're going to multiply 9 times 1, which is just 9, and the x squared comes with us. So this 3x squared y to 0 really just reduces down to 9x squared. So that was kind of a little practice with that. Now let's talk about the negative sign for a second. And we have to remember that a negative sign is equal to negative 1. Okay, if we can keep that in mind, then we kind of know what's happening here, and we're able to look at numbers and know what's really going on. Is it turning out to be positive? Is it turning out to be negative? So here in example A, this is saying that I have a base of negative 3 2 times because it's in the parentheses. So that means I'm going to take 2 negative 3's and multiply them. And we know a negative times a negative is a positive, and 3 times 3 is 9. So this will simplify down to positive 9. Now let's take a look at another example here. And we notice that the negative is not part of it anymore. It's outside. So what this one is telling us is that we've got a negative 1 out here. So I've got negative 1 and 3 2 times. If we take a look at this, there's only one negative there, which means our answer is going to stay negative, and 1 times 3 is 9. Now that may be a little confusing to you. You're thinking, but Mrs. Dorlis, you didn't count out it as a negative 1 here. Well, I could have. I could have said I have a negative 2 times and a 3 2 times. I could have taken this and said that I had a negative and a 3 2 times. So let's say negative 1 and a 3, a negative 1 and a 3. But still, you see a negative times a negative. 1 times 3 times 1 times 3 is still 9. And there's only 2 negatives, so it still stays positive 9. So you see that idea that negative sign equals to 1 is really true. Now let's take a look at this one last example here about the negative sign. Here we have negative 3 squared. So if we think about the negative sign, when we see the negative sign, we want to think of the words opposite of. It's almost like looking at the number negative 4. Negative 4, what is the opposite of 4? Well, the opposite of 4 is a negative 4. So here we're saying we want the opposite of whatever 3 squared is. Well, again, that negative 1 is out there. It's not part of it. And then we have 2 3's. So if we know that 3 squared is 9, the opposite of 3 squared would be negative 9. And again, we can see there's only one negative here. So be really careful with the use of the negative sign and really look where it's at so that you know if your answer turns out to be positive or negative. Now let's talk a little bit about multiplying. Now when we multiply and remember about our base and our exponent, we got to know what we're talking about. So we have here 2 to the third times 2 squared. And when the bases are alike, we're going to add the exponents. And here I'm going to prove that to you. So we know that this is 3 2's. So 2 times 2 times 2. And here I have 2 more 2's. We can see that I've written down 5 2's. Okay, I'm going to put that over here, 2 to the 5th. Now, if we follow this rule, the bases are alike, we add the exponents. We can see that they're both 2's, can't we? So if we keep the base and add the exponents, 3 plus 2, well, 3 plus 2 is 5. And we're going to get 2 to the 5th. So you can almost imagine in your head, 3 2's, 2 2's, all together I've got 5 2's. So that might help there as well. Let's practice this a little bit. Here I have m to the 5th times m to the 7th times m to the 3rd. If I add them all up, because they all have the same base, so I can put them all together, 5m's plus 7m's plus 3m's all together are 15m's. And we can't evaluate it any further because the base of m really doesn't allow us to do that. Here I have another example, 4a squared times 3a. Now when we're looking at this example, we have to look at what goes together and what's really happening. If I was to rewrite this, this is 4 times a squared times 3 times a. And what are the things that go together? Well, the 4 and the 3 go together because they're numbers and they're alike. So if I just did 4 times 3, I know that 4 times 3 is 12. Here I have 2 a's, here I have one more a, and even though there's no number out there, we know that there's one there. So altogether, we have 3 a's. If it helps you to put a little 1 next to these ones when there's nothing there to help you see it, please feel free to do so. That sometimes helps to keep things from getting confusing. In this example, it's very similar to example 10. We have 4r to the 6th s times 7r to the 3rd s to the 5th. So once again, we're going to take our numbers, 4 times 7, and 4 times 7 is 28. We're going to count how many r's we have. Here in this first one, we have 6 r's. Here in the second one, we have 3 r's. So 6 plus 3 will give us 9 r's. We have some s's as well. So we're going to look here. Here there's one s sitting there all by itself. And here we have 5 more s's. All together, we'll have 6 s's. Now, dividing is going to be the opposite of multiplying. So instead of adding the powers or adding the exponents, we're going to subtract those powers from each other. We're going to subtract those exponents. And again, I'm going to kind of prove to you what I'm talking about. So here if I had 5 2's, and here I have 3 2's. Now we know that any number over itself equals 1. So here's 2 divided by 2, that's 1. 2 divided by 2, there's another 1. 2 divided by 2, here's another one. So basically, I've got 1 times 1 times 2 times 2. Well, that just gives me only 2 2's. Now, if I only have 2 2's, I know that 2 times 2 is 4. Now, could we have done this the other way? Could we have looked at this and said, hey, I've got a base of 2, the bases are the same, so I'm going to keep it, and I'm going to subtract them. 5 take away 3. 5 take away 3 gives me 2. So we'll write here. Now, I told you we were going to come back to this, didn't I, about zero exponents. Let's think about what this means. Okay? Let's put out, this is 4 times 4, and the bottom is 4 times 4. We know that these are giant ones, aren't they? 1 times 1. And 1 times 1 is just 1. And if we think about this, what was this in terms of keeping the base the same, which is 4, and this would be 2 minus 2. Well, what is 2 minus 2? 0. So we can see that any number to the 0 power equals 1. So this is kind of how we prove why anything to the 0 power equals 1. So hopefully that was worth waiting for. Okay, let's continue on and do some more examples. Here we have example 12. Example 12 says, let's keep that base. It says 4 to the 12th power divided by 4 to the 8th power. We're going to keep that base of 4 and say 12 take away 8. 12 take away 8 is also 4. Now, because this is an exponent that's 4 or less and a base that we can't evaluate, we have to keep going. 4 times 4 times 4 times 4. 4 times 4 is 16. And 16 times 16 is 256. So sometimes we have to keep going, so we have to be on the lookout for that. Okay? Here we go in example 13. I have w to the 18th divided by w to the 13th. Same base, so we keep the w. And all I have to say is 18 take away 13. That leaves us 5. So the exponent is 5, and we're done. So, hope that didn't scare you. What happens when you add the exponents and it turns out negative? Do you remember what to do? I know we talked about it a little while ago, but hopefully you remember. Here we go. We have here a base of n, both n's, n to the 14th divided by n to the 24th. We're going to keep that n base, and this is 14 take away 24. So let's think about that. 14 take away 24. That turns out to be n to the negative 10. Well, since it's negative 10, we cannot leave our answers that have negative exponents. They are not finished yet. So we would have to take the reciprocal of this number and put 1 over n to the 10th. Now we're done. We always want to make sure our answers are in positive exponents. Here I have an example 15. We're going to split this up a little bit. Sorry about that. Let me redo that. Kind of got a little away from me there. I was trying to separate the numbers from the letters. There we go. Because really, we've got a couple things going on here. And remember, numbers go with numbers, variables go with variables. So here we have 6 divided by 18. And we know that 6 can divide into both numbers. Because we're dividing basically by a fraction of 1. When we divide by a fraction of 1, it doesn't hurt it. So here I have 6 divided by 6, which is 1, and 18 divided by 6, which is 3. Now I go back over here, and here I have b to the third divided by b to the third. Hopefully, when we just look at it, we can see that they're exactly the same. If they're exactly the same, then this is equal to 1. I don't really need to put it over here because 1/3 times 1 is just 1. But again, by definition, those bases, keep the base of b, exponent is 3 minus 3. That's going to be b to the 0, which is equal to 1. 1/3 times 1 is still 1/3. Okay? Now, one last thing. I know it seems like a lot, but let's kind of go through this. This is what we call a power to a power. This is taking it a little bit further. So think about what it's saying. Parentheses means to multiply. So here I have 2 squared 3 times. Let's do that. 2 squared 3 times. And then this is going to keep breaking down, isn't it? I've got 2 2's here, I have 2 2's here, I have 2 2's there. Altogether, base of 2, I have 1, 2, 3, 4, 5, 6 2's. So 2 to the 6th power. Well, there's an easy way to do this instead of doing all of this work. We can keep the base, which is a 2, and all we have to do is multiply when we bring a power to power. And that's why I put this little thing here. Remember, parentheses means to multiply. You can see there's parentheses between the 2 and the 3. Those exponents. It's like taking the exponent and raising it again to another exponent. And 2 times 3 is 6. And we can see that these are exactly the same. So if we remember that rule, that will really help. Okay, let's try a couple of quick examples here. Here I have g to the 5th raised to the 4th power. Based on this idea, this is a base of g, and 5 times 4 is 20. It's that simple. Here's one more. Here I have, I'm going to put this one over here a little bit so there's some room, 2x to the 5th 3 times. Well, if we follow our rule, we remember that the x part's easy because it says, hey, I've got x to the 5th 3 times. Well, x to the 5th 3 times is x to the 15th. Remember, we've got to treat the numbers and the variables separately when we've got multiplying going on in here. So this is saying I have 2 to the 3rd power. Okay? 2 to the third power x to the 15th. We know that 2 to the third power we have to reduce. 2 times 2 times 2, which is 8. So our final answer is 8x to the 15th. If you don't believe me about this, think about this for a second. This is saying we have 2x to the 5th 3 times. 2x to the 5th times 2x to the 5th times 2x to the 5th. We can see those 3 2's there, can't we? 2 times 2 times 2, there's our 8. 5x's, 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 altogether 15x's. Now I know at this point your mind's going a little crazy, so I just want you to watch this last one just to kind of get an idea about what we were talking about earlier about positives and negatives. Now, here I gave you two examples. Negative 2 to the third raised to the third power, that's going to equal negative 2 to the ninth. This one, negative 2 to the fourth power, and I'm telling you that this is positive 2 to the 16th. Boom. Why? Why does that happen? Well, let's take a look at this. If we do these numbers, right? 3 times 3. We know 3 times 3 is 9. This is going to stay negative. It's going to stay negative because it's odd. When the numbers are odd, the exponents are odd, it's going to stay. This will give us 9, but this is saying, hey, I got 3 negatives. If we've got 3 negatives, it's going to stay negative because you need an even number of negative signs in order to become positive. So here, 4 times 4 is 16, and it's saying, hey, I need 4 negatives. Well, 4 negatives, we know, will give us a positive because every 2 negatives is a positive. I think that's about it. I think I have one hiding here, but we'll take a look. Nah, we won't worry about that. Okay, that's the end of this lecture.